Then, first of all, let me thank the organizer for allow us to share our work in this night workshop. And the focus of my talk is exceptional points from a hybrid physical system, and I shall highlight some connections to the time evolution of initial prepared states, particularly its behavior at long intervals of time. Hybrid quantum circuits combine two or more physical systems intending to harness the advantages of each component of it. An example of this type of device was given 10 years ago by Su and collaborators, and it consists of a superconductive flash cabinet interacted with an ensemble of nitrogen vacancy centers in diamond. This is the experimental device, a crystal of diamond, and on the top of it, a superconductive flash cabinet. From the experimental point of view, the Hamiltonian of the model can be understood by three terms: the term containing the qubits, the term containing the MBs, and the interaction among them. The superconductive flash cabinet consists of an aluminum superconducting loop with three Josephson junctions, and when an external magnetic field is applied through the loop, the system behaves as a two-level system that can be modeled as this simple Hamiltonian, where these are Pauli spin half operators, epsilon is the energy bias of the circuit, and delta is the tunnel splitting, and by a transformation to new spin operators, this Hamiltonian can be diagonalized, and the eigenvalues are related through this expression to the energy bias and the tunnel splitting. The MB centers in diamond are defects consisting of the replacement of a carbon atom by a nitrogen atom, and the neighboring site is empty. The structure of the ground state of this system is a spin triplet with spin 1 that, in absence of external magnetic field, these two states, the projections +1 and -1, are almost degenerate, and the system can be modeled by a two-level system. The energy difference between these two levels is of the order of 2.88 gigahertz, is given by D, and is comparable to the transition frequencies of the qubits. The usual way to introduce an interaction between the qubits and the embeds is this direct product of the spin component zeta of the qubits and the spin component x of the MB centers. We have proposed to modify this interaction to take into account the other impurities in the crystal, like neutral nitrogen atoms that receive the name of P1 centers, that are responsible for the loss of coherence of the MB system. We propose that to create an MB in the excited state has not the same probability as to annihilate it in the excited state and create it in the ground state. The asymmetry parameter we consider as real, and we call it alpha. Let us give a qualitative way, a qualitative form of the spectrum we have. In absence of these interactions, the superconductive flux qubit behaves as a two-level model, and if we take a system with two MBs, the collective states of the two MBs give three different energies. When this interaction is turned on, these states split, but now, as this interaction is not Hermitian, it may happen that some of these states acquire a width, that is, the eigenvalues should be not real but complex. To look at the type of spectrum we shall have, we have to look at the form of the Hermitian conjugate of H. Basically, it changes S plus in S minus and S minus in S plus. As alpha is a real parameter, this operator is the transpose operator of H. So both operators are isospectral operators. If they are isospectral operators, the only possibility is that the spectrum be real or that there appear pair of complex conjugate eigenvalues. It is straightforward to look at the similarity transformation among both Hamiltonians, and we shall work in a basis product of the basis of the qubit and the collective basis of the MBs. Let us look at a particular example. We have two MBs. The energy B is fixed to 2.88 GHz. We have choose E to 0.026 GHz, and we have fixed the value of delta over 2 with the value of D. And we have defined an adimensional constant related to the interacting constant G, gamma. We have plotted here the real and imaginary part of two of the eigenvalues we have obtained by varying gamma and by varying the asymmetric parameter alpha. We see that these two eigenvalues coalesces to the same value, and at this point along this curve, we have exceptional points, a regular pattern of exceptional points. Both the eigenvalues and the eigenvectors are coalescent. This pattern, this regular pattern, can be extended if we vary now delta with V. The previous figure corresponds to this curve. Now, if we vary delta with V, we have the other curves. Clearly a nice regular pattern of exceptional points. To look to the time evolution of this system, we decide to work with the green function formalism, and the Fourier transform of the green function gives us the information of the time evolution of the system. We shall not enter in details, but you can look at the paper or the reference therein. Let us show you, this matrix is called the transition matrix, and the elements of it give the probability as a function of time of each state of the previous basis. Just to remind, if we fix G to 0.02 GHz, we have this sketch for the real and imaginary part of the previous exceptional points, And we see that at this point, near alpha 0.9 and alpha 1.3, we have exceptional points. In this intermediate region, the eigenvalues are real. At this site and at this site, the eigenvalues are complex. The transition probabilities for each of the states of the basis show an oscillatory pattern in this region and tend to reach a constant value as a function of t in the complex spectrum region. If we look at the long interval of time and we look what happens with alpha, this is the way the probabilities behaves as t takes a large value. Let us look at the survival probability of the problem. We shall begin with an initial state prepared as a product of the initial state of the qubit and of the base. We shall propose that the qubit in the initial state is at the ground state, and for the n bits we shall take a coherent state. The overlap of the time evolution of this state with the initial state gives us the survival probability, and here we have plotted some of them. For instance, for theta equal p over 4 and phi equals 0, in the steady state, that is, after a long interval of time, the survival probability as a function of alpha shows a maximum at the first exceptional point, and it goes almost zero at the second exceptional point. For theta equal p, we have the other, at the first exceptional point, the survival probability is small, but it is large at the second exceptional point. So we can work with different initial states and different values of parameter alpha. Remember that alpha equals 1, the hermicity is recovered, and in function of them, different states will survive after in the steady state. At the sessional points, we observe that the mean value of observables does not obey an exponential law. Why? Because let us take this simple example, and at the central points, the Hamiltonian is no longer diagonalizable. So we have to use a Jordan form. The use of the Jordan form can be seen in this matrix of the transforms G, and is clear by this polynomial in T in this matrix entry. As an example, let us take the case of an initial state with the qubit in the ground state and the NBs in a coherent state with theta equal p over 2 and phi equals 0. And we see clearly that the probability, the survival probability, departure from the exponential law. We have, in this simple model, we can get an analytical result, and it's clear that if we the two dominant order in T, this will approach a constant value. Let us now look at the squeezing parameter.
You have 2 minutes left.
Sorry?
You have 2 minutes left.
Okay. Squeezing states are correlated states, so that one of the components of the spin is the fluctuation of one of the components of the spin is minimized or is under the uncertainty limit, and we see that for the region of real parameters, the system is squeezed. Instead, in the region of complex spectrum, the system is not squeezed. There is an interesting feature that is, if we plot the mean value of the spin, there is a point, particular point in alpha, for which the mean spin takes the value 0. Why this is interesting? Because a long time ago, Agarwal proposed to construct a spin Schrödinger cat states by superposing two coherent states. This superposition of coherent states has mean value of spin equals 0. So we look at the time evolution of a coherent initial state at this particular point, and we find out that the steady state is a cat state. We look this in the 2NB system, and we find a regular pattern of cat states. And when we look at the states at system with large number of in, the regular pattern was still present. Now let's come to our conclusions. We show that in this type of hybrid physical systems, it is possible to obtain exponential exceptional points, and the existence of exceptional points reflects in the vicinity, in the non-exponential decay law in the vicinity of them, and that it is possible to generate steady robust states, as an example, Schrödinger cat states. Thank you for your attention, and well, it was a pleasure to give the talk at this nice workshop.
Thank you very much, Marta, for this interesting talk. Are there some questions?
May I have a comment?
Yes.
It's fantastic when one sees that those things are coming from real world experiments. And my question is whether you could make also arrangement where there will be some time dependence of the structures.
Time dependence of the structure, yes. I can share the work. I don't know how to, let me, okay. For instance, these are dependencies of the survival probability as a function of time near the exceptional points. This is in the regime of a real spectrum. These A, B, E, and F are in the regime of complex spectrum. In the regime of real spectrum, we observe oscillations, while due to the fact that the spectrum is formed by pair of complex conjugate states, it is clear that at large times there would be a constant behavior of the values of the survival probability, and this is also for the squeezing parameter or the mean value of S. This is in the regime of complex spectrum. We see that at the early times in the evolution there is squeezing, but at large times the squeezing is washed out.
Okay, thank you.
I have a super short question, if I may. So at long times, no, we expect the system to have reached its steady state. So it should correspond to an eigenvalue in, well, in the Liouvillean or in your effective Hamiltonian, no, which corresponds to 0, which describes the steady state, no. And so when you show the plot of the survival probability, how you said you took at a long time, a large t, but at large t, you should have reached a steady state, no? So how does it work? If the answer, you think it's too long, we can continue the discussion about.
Well, okay. After a time of 6 microseconds,
Mm-hmm.
we obtain that every physical quantity reaches an steady state. That is, it remains constant in time.
So there's all
Uh,
survival probabilities, they go to 0, no?
Also,
All
uh,
survival probabilities, they all go to 0, no? Because there is no probability to return to the initial state if you are in the steady state.
in some regimes of parameters,
Yes.
not in all regimes of parameters. Near the exceptional points, we reach a constant value for the survival probability. Because as the spectrum is complex pair conjugate, we have also gain and loss. And in some sense, gain and loss compense in the steady state to give a constant value of the observables.
Okay. Okay. Thank you very much. Okay, so we should go to the next speaker. Thank you, Marta, for this nice talk.